Alrighty, welcome to Beaumont's development segment on stamp, brought to you by myself, Dave Corsi. So prior to getting into the content for today, let's get to know each other a little bit. So my career started in 2005, where I attended Erie County Technical School for drafting and design. This is where I began to get my passion for design-related work. In 2006, I received an opportunity for a mold design internship in Girard, Pennsylvania, in a small company called Residual Design. That's really where I learned the logistics of mold design at a small scale, began using, at the time, Wildfire and Pro-E, which was later on purchased by Creo. And I really knew at that point that I enjoyed doing plastic injection molding design work. So from there in 2007, I made the decision on attending Penn State Barron for plastics engineering technology. In 2009, I received an amazing opportunity to work with one of the best companies in the world, Beaumont Development. And I got an opportunity as a design and simulation intern at that time. In 2011, I graduated with my degree in plastics engineering technology from Penn State Barron, that is the Erie, Pennsylvania campus. 2011, upon graduation of the Penn State degree, I started full-time as a design and simulation engineer here at Beaumont. Since then, we've been busy. 2011, gained my associate's certification in Moldflow, 2016 professional level, and in 2019 my expert certification from Moldflow. 2020 I gained my certificate to GM certified Moldflow analyst. So altogether I have about 20 years in the plastics injection molding industry, really with my primary focus on simulation design work, as well as mold design. So that's a little bit about my professional career so far. I'm also a proud father of two with a beautiful wife. Love outdoor things, and really just enjoy making other people happy and running an awesome department here at Beaumont. But that aside, let's get into it. Alrighty. What is STAMP? So Autodesk classically loves acronyms. So STAMP stands for Shrink, Test, Adjusted Mechanical Properties. So what is it? It's a corrected shrinkage model used in a 3D analysis. And we'll talk a little bit more about that as we go through this particular presentation. Why would we use STAMP? Well, that's pretty obvious. We want to use a model that makes the mold flow warpage predictions more accurate. That's why we're here. How does STAMP work? So STAMP recalibrates the mechanical properties by leveraging the CRIMS tested data. So what mechanical properties is it actually looking at? Well, let's look at the chart here. This screenshot was taken from the Autodesk window under the material properties. So the mechanical properties are modulus, Poisson's ratio, shear modulus, and coefficient of thermal expansion. So that's really what STAMP is doing. So it's recalibrating those mechanical properties to leverage the CRIMS data. But we have to ask ourselves, what is CRIMS? So before discussing STAMP, we need to better understand where this data is actually coming from. So another acronym, Moldflow loves acronyms. CRIMS stands for Corrected Residual In-Mold Stresses. So if you're like me, in order to understand what a test is, I like to dig into the logistics of the test itself. So let's discuss the testing procedure. So we can really define this in 7 steps, the CRIMS testing procedure. Number 1, it's a physical shrinkage plaques are molded on an injection molding machine. This screenshot down here in the lower right hand corner of your screen represents the mold, exterior of the mold. You can see here, this is an image of the actual parts that are molded on that injection molding machine. It's a single cavity tool, cold sprue fed to a cold runner, to a fan gate, to a flat plaque. And the flat plaque dimensions are approximately 2 inches by 6 inches with varying thicknesses. And we'll talk about the varying thicknesses here in a few moments. Step 2 in the testing procedure, the stationary platen of the mold, which again is in the lower right-hand corner, is inscribed with a grid pattern. And you can see here in the image on the screen here, the grid pattern, if you look closely, you can see that grid pattern is etched into the stationary platen. I also provided a 3D model of the 2x6 plaque just so you can get a general indication of what that grid pattern looks like. And the importance for that grid pattern is so that the optical device can measure the differences in dimension pre-condition versus after condition. So step 3, test plaques are produced under a wide variety of molding conditions. So I mentioned that this is a physical test, so it's important that you capture a wide variety of molding conditions. So the varying conditions are melt and mold temperatures, flow rate, hold time and cooling time, hold pressures, and varying part thicknesses. Again, we'll take a look at that here in a few moments. Step 4, post-molding. So after the samples are molded, post-molding, the samples are annealed for a nominal 1 week duration, and this just allows stress relaxation over time. So we're not measuring samples right at the end of the cycle, molding cycle. We want to make sure that if it is a semi-crystalline material, we give adequate time to go through crystallinity and changes over time. So in a lab environment, those samples are annealed for a duration of 1 week. And then step 5, a linear coordinate optical measuring device is used to take the actual dimensions. So really what that device is doing is it's evaluating the grid pattern from its initial CAD nominal position to any final resting position. So essentially it's shrinked down state. So we're evaluating a position that was CAD versus a position after shrink. So next we go to Moldflow, and let me get these animations going. So flow simulations are performed at each of the measured molding conditions, and these are used to predict a shrinkage. So Moldflow goes through the same process of evaluating all the thicknesses, all the molding conditions, and Moldflow is then compared to the samples that were produced on the injection molding machine. From that, a regression analysis is used to measure the predicted shrink performed and determines the coefficients of shrinkage. So essentially, if you're not familiar with a regression analysis, it's just a mathematical method of sorting data. So we're defining independent and dependent variables, and we're fitting those variables to a curve to understand the CAD nominal value to post shrinkage values, and then also comparing back to Moldflow. Then finally, step 7, the measured values are inputted into the simulation properties tab within the material UDB file. So at this point, let's go ahead and take a pause from the PowerPoint because I know that can get boring and cumbersome at times. And let's get taking a look at the Moldflow analysis. So where do you find the CRIMS tested values? So on the left-hand side of your Moldflow window, as you can see on the screen, in the Study Task Manager bar, 4 lines down is the material file in which was used for this particular simulation. If we go ahead and right-click on that, Edit Properties, now we have a whole range of really useful information on the material. But for today, what we're going to concentrate is on this Shrinkage tab. Okay, let's go ahead and click that, and let's make it full screen so everyone at home can see. All right, so the Shrinkage tab, this is the first indication whether or not your particular material has CRIMS, so corrected residual in-mold stresses data. Now, if the particular material file that you're using does not have crims, these areas simply will not be populated. So since it is populated, we do have crims. You can see it on the top of the screen. Also below that, side note, this is where you will change from the uncorrected residual stress model on your 3D analysis, right? The top line is for midplane and dual domain. The bottom line is for 3D analysis. This is where you'll switch from uncorrected residual stress to your stamp model. Just take mental note of that. So within this data set, there's oftentimes some really good information. So first and foremost, it graphically represents the series of temperatures that were used to measure those samples. So melt and mold temperatures, in which I previously mentioned, along with flow rates. So there's always varying flow rates to see how that affects the shrinkage of the plaques as well. But another category that is extremely important is thicknesses. So this particular data set was evaluated at several different thicknesses, starting at 40 thousandths or 1 millimeter, and goes all the way to 3 millimeters. So we're evaluating sample sets at varying thicknesses. The reason why this may be important to you as a user, or if your interpretation looking at results, is that if you have a part that is 3 millimeters thick, then you may want to focus on the shrinkage values that are on the bottom segment of this chart. Now, if your material wasn't flowing through a 3 millimeter thickness, you obviously wouldn't want to evaluate it at a 1 millimeter thickness. So be cautious of what you're looking at. And you can begin to better understand the processing parameters that are in the data set when evaluating this information. You can even go a step further and fine-tuning it from temperature and pack pressure, that you would have a sense of in that particular application. When you're molding, you can fine-tune the temperatures that you may be within to grab the parallel shrink and perpendicular shrinkage value. But regardless of that, we're kind of getting into the weeds in a sense. The top chart here gives you an indication of average values. So of the data set of the CRIMS data that's published on the bottom of the screen, it just takes a minimum parallel and a maximum parallel, takes an average. That's how you get the observed nominal values. Likewise, on minimum perpendicular and maximum perpendicular directions, takes an average and post that to the top of the screen. So let's get back into the PowerPoint here. All right, so we discussed where you would find the CRIMS data. Now, a fun fact is that Moldflow has approximately 13,000 materials in the Moldflow public database, which is a huge amount of materials. But understanding that there's probably closer to 100,000 materials of variants of different materials in the world, 13,000 compared to 100,000 is fairly low. But if we take that one step further and look at the material files that have CRIMS, we have about 5,000 materials. So we have 100,000 materials in the world. We have 13,000 materials in the Moldflow public database. And of the 13,000, we have about 5,000 materials that have shrinkage data generated. That's the CRIMS information that I'm talking about, which is absolutely exclusive to Moldflow. So let that sink in. As an analyst selecting the material, we really have things up against us. We're at the liberty of the public database. But the good thing is, if you do have a material that is not necessarily tested in the public database, that's certainly a service here at Beaumont we can help you out with. So, anyways, moving on. Are you using CRIMS? Prior to 2024, this was probably one of the most frustrating questions in my 20-year experience as a Moldflow analyst that I got. You've been on the calls that you have a customer that insists on running simulation with CRIMS, but they have absolutely zero clue what CRIMS is. Then you have to go on to this long, drawn-out, lengthy explanation to talk the customer off the ledge, right? We've all been there. What it is, why you use it, and maybe for that application, why you're not going to use the CRIMS data. So let's take this for example. You have a fairly thick, chunky part that has a poor match percentage, and the material file simply does not have CRIMS, right? It's not one of the 5,000 materials. So we need, in that situation, we need to run a 3D analysis. But with that 3D analysis, we're forced to run the uncorrected residual stress model. CRIMS just isn't an option. But luckily and fortunate for all the frustrated Moldflow analysts out there like you and I, Moldflow in 2024 announces STAMP and announces the ability to leverage the CRIMS data. And just announced a few weeks ago in the 2026 version release that is available now, STAMP is now the default 3D shrinkage model. So take note of that. Once you upgrade your operating systems, 2026 STAMP will now be the default. So another good piece of information to keep in mind. So let's get back to STAMP. So we understand what CRIMS is. It's an excellent data set. It comes from real world molded samples, which is absolutely awesome. So what is STAMP? So there's really 8 facts that I want everyone to take away from this presentation to have somewhat of an understanding of what STAMP is. So STAMP is a variant of the uncorrected residual stress model. As a reminder, that is the prior to 2024 uncorrected residual stress model is the default 3D model to solve for shrink and warp. 2, STAMP model uses measured shrinkage data to recalibrate the mechanical properties. I kind of mentioned this earlier. We're actually recalibrating the modulus, Poisson's ratio, and coefficient of thermal expansion. That's what we're recalibrating in this method. 3, you can use STAMP for all thermoplastic materials, but you have to have the CRIMS data. This isn't something you can use for thermosets. This is exclusively to thermoplastic materials as of now. 4, the STAMP model works for both unfilled and filled polymers. So you can run it on any thermoplastic, unfilled or filled materials, regardless of the filler aspect ratio, talc, glass, long glass. You can leverage the model for all those situations. But I should note on the fiber aspect is that the fiber filled materials will only have the CTE values that are calibrated according to the measured shrinkage data. So what that means is the CTE values that are listed in the mechanical properties, you can see the coefficient of thermal expansion. Assuming these categories are populated, that's what the solver is using. It's not using the properties listed in the fiber model. So take that note as well, because that's important. All right. Back to the facts. Since the data, and this is really important, number 5, since the data is derived from measured test plaques in the flow and cross flow directions, we're actually able to capitalize on anisotropic shrinkage tendencies. So that's really cool, because it's not just a standard isotropic shrinkage tendency, it's an anisotropic shrinkage tendency, which takes the polymer shrinkage into consideration in the calculation. So that's really important. 6, STAMP can be used for any type of 3D analysis. And what I mean by that is small deflection, large deflection, and or a buckling simulation. STAMP works for both semi-crystalline as well as amorphous materials. And number 8, no additional testing is required, assuming your material was tested with CRIMS. So without the CRIMS data, I know I've mentioned it 3 or 4 times, you simply cannot take advantage of the STAMP solver. Alrighty, so facts aside, let's get into some real world data, starting with the Autodesk published study where we're evaluating a talc-filled TPE. So let's explain what we're looking at here first on the screen. So we have on the left-hand side the TPE in the flow direction, and on the right-hand side we have the TPE in the transverse to flow direction. So flow direction versus cross flow directions. We have each of the two plots, left and right. We have 3 data samples. So the blue curve is the measured data. The red curve is a residual stress model. So that is a 3D analysis ran with a default uncorrected residual stress model. And on the green curve here, we have stamp. Vertical axis is evaluation of percent shrinkage, and the horizontal axis on both of these graphs are at varying processing conditions. I should also note that there's 3 thicknesses evaluated in this sample set as well, 2 millimeter, 1 millimeter, and 3 millimeter shrinkage tab thicknesses. So let's start by looking at flow direction. So the 2 by 6 inch plaque in flow direction. It's pretty obvious that the evaluation of the processing conditions between 15 and 20 is observing a influx in shrink. So that could be maybe a temperature variation, could be a thickness variation, causing an influx in percentage of shrinkage. Now, looking at the red curve, which is the default 3D model, we're simply not picking up on that difference. Lo and behold, running the same study, so it's a duplicated study ran with stamp, we now have the ability to predict that inflation in volumetric shrinkage ran between the test samples of 15 and 20. Likewise, on the right-hand side of the screen, looking at the transverse the shrinkage directions, on the top curve, it's pretty obvious that the 3D analysis default residual stress model isn't doing a great job. But again, we see these curves almost aligning in sample sets, processing sample sets 15 to 20, which is doing a really nice job of picking up on those trends. So overall, the shrinkage magnitude is substantially better with stamp. And we're able to really have a better capture of the anti-isotropic tendencies with sample sets 15 to 20. If we look at this similar data just in a different approach, so evaluating the air percent residual stress versus stamp. So again, we're looking at the default 3D. We're concentrating on a 3D analysis, and we're looking at the default model pre-2024, and we're looking at stamp. And the first data set we have here is with unfilled materials. So the purple dots on the screen represents a polypropylene material, no filler. The green triangles on the screen represents a semicrystalline material, no filler. And the red boxes on the screen represents an amorphous material. So we fitted the graphs with a trend curve. On the vertical axis is stamp. On the horizontal axis is residual stresses. And we're able to evaluate below the curve, stamped is deemed as a more accurate prediction. Above the curve, stamp isn't doing quite as good. And we can very quickly see on both the flow direction and transverse to the flow direction, the polypropylene and other semicrystalline materials are trending better with stamp. Now we do see with the amorphous materials, they're hanging above the curve a little bit, but the vast majority of them are beneath the trend line, which suggests that stamp is doing a better job. And we can look at the similar evaluation, but with fiber-filled materials. Again, polypropylene, blue dots. Other semicrystalline materials are the green dots, and red is amorphous. Filled, this is a filled study. Again, Below the curve, stamp is doing a little bit better job. Above the curve, stamp is doing a little bit worse. So based upon that information, as an analyst, that's certainly giving me more confidence in the solver's ability to accurately predict warpage. That's mainly why we run Moldflow simulations, to accurately predict warp. So if we go into our first case study, which is a tray, and this particular tray is like your iconic midplane or dual domain analysis. That's what makes this first case study so unique, because most experienced analysts out there would choose a midplane mesh or a dual domain mesh based upon the match percentage and reciprocal match percentage in this particular study. So this part was molded in the controlled lab environment, and the part itself exhibits a buckled twist shape as shown. This posted note on the surface is the flat surface. Holding this back corner to the flat surface, we have a lift of about 17 millimeters, which is quite substantial, really. Running that model with the 3D analysis, again, dual domain or midplane, they do pick up on these trends. This image on the top right is the 3D analysis ran with the residual stress, and it's pretty clear that it misses the trends, right? It's really not doing a great job of predicting the trends at all, for that matter. But ran using stamp, now we see the nodal shape of the part, again, from surface. We've put a few anchor points in this particular model. So we're holding that back corner to the lower surface as we are in the image of the actual part that's shown on the left-hand side here. And now we can see not only is the trend a positive match, but the magnitude's getting pretty darn close. 17 millimeters versus 15.85. So that gives us a lot of confidence. And the reason why this is so important is because one of the most difficult decisions that I personally have as a Moldflow user is understanding what mesh type to select for that particular application. And really it comes down to a lot of the Moldflow analysis that we run. We'll actually run multiple solvers or mesh types and compare the results. So what this gives us is confidence in saying that, okay, now we have confidence in a 3D analysis to accurately predict magnitudes and trends within reason. So if we were to run a 3D analysis that maybe should have been ran as a dual domain, we'll still get pretty close to the warpage. So the main thing that Autodesk is doing is getting the midplane and dual domain aspect to come closer to the 3D aspect, which is extremely important. So let's go ahead and take a look at a second case study, which is a automotive trim piece. This particular trim piece is about 42.5 inches long, molded from a Cyclax ABS material, and the processing conditions are as listed on the screen. So the first question, what mesh type should we use? So at that point, we begin looking at the material file and also the mesh. So we start with the material file itself. We understand that it does in fact have its CRIMS tested values. All the fields are populated. So that's a check mark for dual domain as well as midplane. But we begin looking at the part, which looks like a constant nominal wall part, but we look at the core side of the tool and it's scattered with B-side rib structure. And what B-side rib structure does on a fairly flat part is it disrupts the match percentage. So match percentage and reciprocal percentage. It's what the outer triangles are looking at the inner triangles, and they're trying to match up 1-to-1 for an accurate prediction. So the general rule published by Autodesk is to maintain a match percentage of 85% or higher for a midplane or a dual domain. Lower than that, you should really run a 3D analysis. So we are lower than that. We're really close to that, but we are lower than that. So this is one of those situations as an analyst, we have to make a decision. Will we be running a dual domain or midplane or 3D? But the challenge becomes, in this particular application, what we're forced with a lot is what shrinkage value should I use? So that puts another layer of how complex this situation is. Because we know by looking at the material data sheet at mold shrinkage, which is always difficult to get a solidified number from the data sheet and or the material supplier, 0.4 to 0.6%. The test method, we're really not sure where that came from. It's an internal method, which that makes us all a little bit nervous. We have to ask the person running the tool or designing the tool, do you have any actual molding history? That's not always defined. We don't always have history to compare to. And if we do have history, was it the same material, similar part thickness, ran at relatively the same processing parameters? There's a lot of stars that have to align there. Then we can begin looking at the CRIMS data, which on this particular application, this part's about 3 millimeters thick, so we can evaluate that data as well. We can also look at the average data points that Moldflow has given us. And then after running the simulations, we can look at the estimated values that Moldflow is giving us. And you can get the sense here, it's all over the map. 0.4 to 0.6%. I have values with my 3D analysis running uncorrected residual stresses as low as 0.2%. So I really have a range here from 0.2 to 0.7%. So at this point in time, we go to the simulation, right? We begin looking at the results. What else is different? We notice that the filling progression is different, right? The 3D analysis and the stamp model shows an imbalance where the dual domain isn't necessarily predicting the imbalance. So filling wise, it looks like the 3D analysis is doing a little bit better job. So why is that important to us? We notice that the right-hand side of the part fills becomes hydrostatic. We have a pressure buildup. That may potentially flash in the tool. And then we fill the opposite side of the part where the dual domain analysis showed balance. We also see a pressure imbalance across the cavity. Also could potentially cause issues during molding. So fundamentally, in the filling phase and pressures, there's differences in the Moldflow solver. Also not giving us confidence in selecting the correct linear shrink value to be used in Moldflow. But we move forward as an analyst, right? We have to figure out a solution. We run the analysis and we see that the dual domain is predicting about 0.6%. It has an estimate of about 0.5%. The 3D with the uncorrected residual stress predicts about 0.3%, half of what the dual domain predicted. Then we'll actually notice that the 3D with stamp was predicting about what the dual domain was predicting. So again, those two solvers aligning. But we're still a little bit puzzled on what we pick. So why is this so important? So the overall trim piece had a length tolerance on it of plus or minus about 20 thousandths. Our desired length in the part is 42.6 inches, meaning our tolerance window is 42.62 to 42.58. Had we went with a 3D analysis, which we may have chosen to run a 3D analysis for this particular simulation based upon the mesh statistics, it told us to run a 3D simulation. We would have had a 66% difference in our linear values, right? So what this gives us is, again, provides us confidence. Had we went with the 3D uncorrected residual stress model, we would have selected a shrink value that was about 60% lower than what we should have chosen for this particular application. So these things are extremely important. Case study 3, and I believe our final case study here. I wanted to throw this in as well because I thought this was really interesting. The previous case study was more of a linear shrink application where shrinkage is in the linear direction. This particular case study is really a warpage case study for an out-of-plane movement. A customer came to us with a challenge, warpage. So the problem was the lid to this specific container was warping in the vertical direction. So we start with what mesh type should we use? Again, to the material information, we have crims, check, that looks great. We look at the mesh statistics. We have a match percentage of 93% and a reciprocal percentage of 89.7%. Moldflow tells us that a dual domain analysis should be used, right? We're above the 85% rule. We have crims. Most analysts that are Moldflow users would move forward with midplane and or dual domain. The baseline analysis was ran. Dual domain with crims, the predictions on the screen, we've seen a opposite relationship. The part in Moldflow is actually warping down, but the lid was warping up. So at this point, we knew that we needed to investigate other solver methods to see if we could more accurately predict the shape of this particular component. And we looked at the 3D uncorrected residual stress model, which was in the correct direction, and we looked at the 3D stamp model, which again was in the correct direction. Compared to the physical warp parts, it's very clear the decision was made that the 3D with stamp was an accurate representation of this particular component. Now, why is that important? It's important for root cause diagnostic. So within Moldflow, we're able to very quickly split our screen and look at each component of warpage. So there's three main components of warpage: differential shrinkage, differential cooling, and orientation effects. So by splitting your screen four ways, all effects on the top left corner, we're looking at the top right differential cooling, lower left differential shrinkage, and lower right orientation effects. And we look at the contributing factor or magnitude from each one of these plots, and very quickly we can see that the orientation effects is said to be the largest contributing factor warpage. So now we've gotten Moldflow to predict the shape of the part. We've established root cause, which is orientation effects. Now we can provide the customer, the client, with a list of recommendations to further improve. Some of those recommendations may include material selection, molding conditions, model thicknesses, or gate locations. And of each one of those categories, we have a lot of subset things to look at, but this is a quick example showing and showcasing the ability to leverage a simulation. First, we have to predict the warpage. Had we moved forward with this model, that could paint a very different picture as far as root cause diagnostic and what's causing that out of plane warpage movement. So back to the facts. We want to, again, this is the most important section of the presentation. Take these facts home, take a screenshot, remember these facts, it's going to help you. Stamp is a variant of uncorrected residual stress model. Stamp uses measured data recalibrated. Stamp is used only in thermoplastic materials. Stamp works for both filled and unfilled materials. Stamp can be used in any type of 3D analysis: small deflection, large deflection, and or buckling. It also can be used in semicrystalline and amorphous material. And there's no additional testing required, assuming you have your CRIMS information published in the database. So let's try to wrap it up here. We now have the ability to use a corrected shrinkage model that is based upon physical molded samples and a 3D analysis to improve our warpage predictions. That's what we all want. I'd encourage everyone to try it, test it, and compare it to existing parts and provide feedback. The Autodesk team is very receptive of feedback. They value the feedback of the users. So if you see something that's not quite aligning, get a hold of your Autodesk representative and tell them what's going on. Show them, send them the study files, challenge them to fix it, or provide recommendations to further improve. Now, remember, the injection molding process is said to be one of the most complex manufacturing processes in the world. I think we can all agree that there is no easy button in our industry. There's hundreds of variables that affects the final plastic product. Be mindful of what simulation can and can't do. I'd encourage everyone to challenge both the simulation and the actual manufacturing process. Success is gained from simulation's ability to match the molding process and the molding process's ability to match the mold flow predictions. This is very important. And as a Moldflow user, we need to understand these challenges and continue to provide feedback to the Autodesk development team. So with that, I would thank everybody for spending their day with me, or not their day, their lunch break, or morning, depending on, or evening for that matter, depending on what times they are. At this point, I'm going to switch over to the questions, if we have any. But also, Alex Beaumont mentioned previous to me beginning this webinar series, please remember at the close of today's webinar to take that brief survey. We at Beaumont value our customers' feedback and the general Moldflow user group feedback. Drop us some ideas for future webinars. We're always looking for new ideas. Let us know what you want to learn. We're here to help you. So thank you.